let's do a little bit of Unit 2. Well, some of Unit 2. We're going to leave that, really. Unit 2 is actually, we're going to talk about cloud types. Do you see the white? The white are the clouds. There's kind of a couple different clouds. This is cumulus cloud, the fluffy ones, and then kind of the thin, usually they're flat. These look a little fluffy, but the thin, flat clouds are stratus type of clouds. But doesn't it look like it's raining right there? You can kind of see it looks like it's precipitating. Okay. And depending upon how dry the air is, sometimes it actually evaporates before it reaches the ground, and they call that actually virga. That's just something we're going to be talking about, virga. Not Viagra, virga. So one of the things I want you to start kind of getting in mind, if you didn't already know this, is that anytime you see a milky white cloud, I'll put an L for liquid. Water is liquid. Okay. Down here, you think we have water vapor. I'll put a G for gas. Yes, we do. Okay. The other thing is, this is a good example of, do you see how flat the bottom of this cloud is? That's kind of characteristic of a relatively newly formed cloud. Okay. That elevation we call the lifting condensation level. We'll talk more about that. But a lot of times they have that flat bottoms if they've just arrived. So we talked a little bit about the water cycle in Unit 1, and we're going to dive into the water cycle more in Unit 2. So it's called the hydrological cycle. Hydrological cycle. Yep. And when it says atmospheric source, it's basically how do you get water from the earth into the atmosphere. Okay, basically we have evaporation, okay? And then we have the thing that plants do to a lesser extent to get liquid water into a vapor. And then geospheric sources means how do you get water back to the earth? Precipitation, okay? And then on the next slide, you're going to see that if we have water that's moving on the surface of the earth, we call that runoff. If we have water that's running underneath the surface of the earth, we call that groundwater or infiltration. So here's a nice little slide. I didn't take grab my calculator to show how this balance was, but of course we have evaporation, condensation in the clouds. We'll talk about at what point the liquid goes ahead and drops in the form of precipitation. Okay, one of the awesome things, and I think we're going to see a video here in a little bit, but basically we have a lot of movement, horizontal movement of the rain clouds. So a lot of this we call advection. A lot of this water that starts here ends up over the earth. Okay, water on the surface, water underneath the surface. Hydrological cycle. The next few slides are like, did not we see these slides? And yes, you did see these slides. Okay, we're just going to kind of take just another look at this idea of how water ultimately can be a liquid or gas or even a solid. So that's ice, right? So the thing about matter is all matter is in motion unless it's at absolute zero. Okay, then it has no motion. I think we talked about that last time. So if we dive in and look a little bit closer at water molecules, of course the red atom there is oxygen, and then the two white atoms are hydrogen. And really a water molecule orients itself like this. And some of you, if you've taken chemistry, kind of know the reason that these things kind of spread apart is actually there's actually 4 or 2 pairs of lone pair electrons that kind of scoot them away. But what water does is the oxygen, just because of how its electrons are, is partially negative, and the 2 hydrogens are partially positive. It's what we say polar. If somebody has a polarizing effect, then they kind of take a crowd and they kind of split them. Okay? So water is a polar molecule, but it's a extra special polar molecule. So we have alternating, when water is stuck to another water molecule, we have these kind of alternating, if you call this 1 and you call this 2, molecule 1 and molecule 2, we have this dot, dot, dot right here. That actually is called a hydrogen bond. hydrogen bond. It's a special type of what we call intermolecular bond to stick two water molecules together. That's important because I'll draw it up here just for kicks. The last page, and we talked about this before, which physical phase basically are all the water molecules totally separated from each other?
Yes.
Yep, exactly. So over here, if these are gas particles, they have a lot of motion and they're totally running around. Over here, they have the least amount of motion and they're stuck together. Right, exactly. And I want you to kind of think as how they're stuck together is with these hydrogen bonds. They're moderately stuck together here. Some of these bonds have been broken to kind of make them slosh around in their liquid stage over here. So here's a couple figures from your textbook then. Now water is unique. This actually, does it look like there's a lot of intermolecular bonds, a lot of hydrogen bonds? Those are the same word, hydrogen bonds. Yeah, so actually this is in its solid state. The thing about water is this is liquid water. Okay, when water freezes, it kind of fluffs out, which is unique for solids. Really, oftentimes when they transition from a liquid to a solid, they just keep getting smaller with regard to volume. A solid is a lot of times more dense than the liquid. But that fluffing out actually makes ice cubes float on liquid water. So that's a pretty cool thing. Okay, so if we add heat, we talked about that's a phase change we call melting, right? And the difference between those two, I guess I would argue, and I've seen this before, I would have liked to seen your author draw at least a few, and they're kind of implying a few intermolecular bonds. Okay. Except they're kind of showing the negative partially. I'm just not real thrilled about this figure. But if somebody says you have something in its liquid form, if you have water in its liquid form, you just have kind of some intermolecular bonds as compared to a gas, and fewer as compared to its solid state. But when ice melts, it kind of collapses. Okay, so let's see if this works for us. And the reason I talked about energy for changing phases in Unit 1 was because I wanted to kind of talk about how energy is transferred. In this case, I'm kind of talking about it because I want to get to the crux of I kind of want to focus on these two transitions here in a minute. But we said, I'll put this whole slide up here. We said that as you go from left to right up here, you have to add energy. Okay, makes sense, right? Less intuitive is if you go from right back to left again, energy is released. And I think I might have mentioned this, but you're like, well, where does the energy come from to do the melting or the vaporization? Or where is the energy released to when we have condensation or solidification? And it comes from the environment. From environment. And this would be released to the environment. Just in the vicinity of where those bonds are being broken or released or formed. So this is actually what we call latent heat. Latent heat. I think I might even call it latent heat energy. Either absorbed or released. So I like this figure from the textbook. I like a lot of figures in this textbook. So the pink are actually energies put in from the environment to the water, and the blue is where energy is released from the water to the environment. So, yeah. But what I like about this one, in contrast to your Chapter 2 one, is we actually have some energies here. So for instance, calories, like you eat a candy bar, you get energy. So calorie is a unit of energy. So it takes about 80 calories, I think, is it per gram? I didn't say what unit. But let's just say 80 calories per gram of ice that you want to melt, okay? And if you want to go ahead and take that 1 gram of water and to go from a liquid to a gas, it's going to take 600 calories. So a lot of energy is required to vaporize or evaporate water from a liquid to a gas. But notice that, and actually we'll be talking more about this when we talk about clouds, because what are clouds? Clouds are basically water vapor is condensed. That's what clouds are. Water vapor has gone to its liquid state. So check out the amount of energy that's released. Released to the environment, released to the, basically back to the cloud. A lot of energy. So that's the latent heat of what we say condensation. And I think we talked about this, but it's possible that basically to skip the liquid step. It's possible to go straight from straight from a solid to a gas, from a solid to a gas. Let's see, and dry ice is an example of that. And then it's possible for it to go from, we call that sublimation, it's possible for it to go from a vapor or gas straight to a solid, to skip the liquid state. And a good example of that is frost. All right. Speaking of, so in part 4 or chapter 4, I'm going to talk about things that are already kind of intuitive to you. Basically, when our atmosphere, let's see, I'm going to go this way. Basically, as our atmosphere cools down, okay, we can have basically the water vapor, okay, go into solid, okay, or water vapor go into a liquid. We'll talk about kind of the critical tipping point temperature that water vapor does that. But if you've been doing your weather logs, you guys have been recording your dew point temperatures, that is the critical temperature at which something happens from your water vapor. That's what the dew point temperature is. Okay. So the other day we had this fog. Okay. So a fog is kind of a cloud at ground level. I was looking for questions for you guys to answer at the end of chapter 4, and one of the questions was one that I don't really cover, and I was like, how would I answer that? But there is a difference apparently about how fog forms versus if it was a cloud at upper elevations, but they're similar. That milky white is liquid water. So fog, there's different types of fog we're going to talk about, but one type of fog is called radiation fog. So in Unit 1, we said, when is it coldest? Well, when you have to get up and take your shower, about 6 a.m. or whatever. So it's coldest right before dawn, and again, your cooler temperatures are going to get it to transition from a vapor to one of these other two things, either a liquid or all the way to a solid. So again, your weather logs, you've been recording humidity, and we're really kind of familiar with this term. Humidity, if you think you know what it is, you do. Humidity is basically how much water vapor is in the air. But there's different ways to express that. The most common one is the one that you've been recording, which is % relative humidity. The closer the relative humidity is to 100%, you figure something's going to happen with that water vapor. Okay, it's going to condense or it's going to solidify. So the one you've been recording is this one, relative humidity, or %RH. Okay, and we'll get to that one. Also, dew point temperature, we'll talk about this, but remember that's the temperature at which you need to cool it down in order to get condensation to occur. Basically, the closer your dew point temperature is to the real temperature, the more muggy, the more humid your air is. Okay, if you basically have a dew point temperature that's way down here and you're currently up here, you're like, oh my gosh, it must be really dry air because you have to go all the way down here. So that's kind of how that works. So we need to talk about, I'm going to start by kind of talking about these two, absolute humidity and mixing ratio. Ways to describe how much water vapor there is in the atmosphere. And it has to do with a little math. But this is a cool picture, I think, from your textbook. Cool figure. These cute little ones right here that have the little white, okay, that's water vapor. Water vapor is a variable gas. H2O is a variable gas. The green ones are nitrogen. How do I know that? Because there's a lot of them. Okay. Okay, nitrogen, N2, is a permanent gas, and so is O2. Wait a minute, yeah. I don't know if they really got the 80-20 going on there, because to me that looks like quite a few. I'd have to count them. But doesn't it look like there's not an 80-20 ratio of green to red? Anyway. So my point is, those are all gas particles. So I refer you to this, where you guys told me that gas particles are just crazy. Okay, with bouncing around. If you blow up a balloon, those gas particles are bouncing around, okay? In this room, those gas particles are bouncing around. They are exerting what we call a pressure. And actually, they kind of exert an independent pressure, like nitrogen, oxygen, water, gas particles exert their individual pressure, but then they have a combined effect, combined pressure. So this is to say, so that we're all on the same track, if you guys have been recording your weather log, or you just go to the news and it says the pressure is 30.5 inches of mercury. That's what the pressure is. That's what the pressure of the atmosphere is. They are talking about the collective pressure. So they don't like single it out. Granted, your little cute little water vapor particles probably are not banging too much in there, but they're in the mix somewhere. Okay. So absolute humidity versus relative humidity. Okay, absolute, the word relative means it's compared to something, and we'll talk about what that is. But absolute humidity is a little division problem, and I'm going to show you some examples here. Okay, it's what we call a ratio. So what you do is you take a chunk, a parcel, we do a lot with the word parcel, talking about a chunk of air. That's our parcel. We take a parcel of air, we calculate the mass of water, vapor, in grams, and then we have to get a fix on the volume of that chunk of air, and we divide it, and that gives us our absolute humidity in grams of water to usually liters, I think, or cubic meters of air. So notice that another thing about chunks of air, this is my chunk of air. I've kind of got a little ball of air, okay, my chunk of air. One of the things about chunks of air is compressible. We could take air and squeeze it down. We could take air and swell it up, that chunk of air, okay? So the problem with absolute humidity is basically in the denominator, the divisor, what we're dividing by is the volume. So as the volume changes, so does absolute humidity. It's weird because you're like, absolute humidity changes. Like, wait a minute, is that what? Okay, so something that does not change with volume, and actually we probably do more with mixing ratio than we do with absolute humidity. Okay, so mixing ratio you're going to see here in a few slides and stuff, a table with mixing ratio. Mixing ratio, again, you take a chunk of air of interest, okay, and again you go ahead and you get the grams of water vapor and you put that in the top. But what goes in the bottom now is basically the mass of the other stuff, the mass of the air without the water vapor, the mass of the dry air. This is in grams of water vapor. This is in kilograms of dry air. So your units are going to be grams of water vapor per kilogram of dry air. Okay, so it's a mixing ratio, and this, who cares if, because chunks of air, we're going to see what did that weather balloon do when it rose?
Got bigger.
They got bigger, exactly. Okay, we're going to see chunks of air that go up are going to get bigger. What if a chunk of air goes down?
It's smaller.
It's going to get smaller. It is. And it's kind of like you guys told me all along, if you climb a mountain, the air gets thinner. Basically, as you climb that mountain, the air is thinner, so kind of the little gas particles that were in here, when it climbs the mountain, it's like, hey, dude, the air is thinner up here. I can take my latex and bang my balloon bigger, okay? Down here, the air is thicker, more dense, greater pressure. So basically, those gas particles are going to respond, and they're going to have to kind of shrink down and adjust to whatever the outside pressure is. So that's why it expands as it rises, and it contracts as it falls. So mixing ratio, okay? Grams of water vapor to kilogram of dry air. Okay, so you can see on your figure that actually I have a couple of chunks of air here. These are the same chunks of air. Okay, so we have a chunk of air down here near the Earth's surface that's this big. All right, it happens to be the volume is 1 cubic meter, which is nice. The dry air is 1 kilogram. Oh, we didn't say what the grams of water is. Okay. So all here is what we need to go ahead and calculate the absolute humidity and the mixing ratio. So if we look at what the absolute humidity is, we said it was the grams of water vapor divided by the volume. Okay, so it's 20 grams of water vapor divided by 1 cubic meter. The mixing ratio is, again, grams of water vapor divided by kilograms of dry air. So it just happens to also have the numerical value of 20. 20 grams of water vapor per kilogram of dry air. So there you go. We're going to go ahead and we're going to let this chunk of air rise, and we're going to talk about actually 4 different reasons I think that why a chunk of air would want to rise. And you probably can think of some of them yourselves. So in this we still have basically, I'll go ahead and show you. In this scenario, we still have the same mass of water vapor. Okay, we still have the same mass of dry air, but of course our volume has changed. So since our volume has changed, what's going to change is absolute humidity. So absolute humidity was 20 grams per cubic meter, and now it's 10 grams per cubic meter. But just like we said, the mixing ratio did not change. Okay, the mixing ratio did not change as the volume changed. So like I said, here in a minute when we start looking at, before we get to percent relative humidity, which we'll talk, that's a good way to describe humidity too, we're going to talk about mixing ratio. All right. So evaporation, condensation, and saturation. Okay, so if we want to kind of go back up to here, okay, you guys would tell me from left to right, that's evaporation. You guys would tell me from, as a gas goes to liquid, that's condensation. Notice that here for a while, I'm not really going to worry about the whole solidification. I'm just going to kind of focus on that. Okay. So I like this, I like the figure coming up too, the series of figures coming up. What you're going to see on the next is basically if you have a chamber and you have water in the bottom of your chamber and you basically have a headspace, if you've ever used a terrarium, okay, after a while your terrariums, if you grow plants or don't grow plants, after a while you might even see kind of condensation on the glass, okay, it kind of makes its own little water cycle, okay. So if you allow your terrarium to go long enough, you're going to see this on the next slide, what will happen is if you have a dome terrarium, okay, what will happen is what we say the rate or the amount of evaporation is equal to the amount of condensation. Okay, if that's the case, if those arrows are equal, kind of showing that evaporation is the same as condensation, it's very dynamic. The same water particles that are liquid don't always stay a liquid, they kind of go through a cycle. If that's the case, then we call this an equilibrium. And if that's the case, then we say that the air above here, this air right up here, is saturated. Sometimes we say the ground is saturated. Well, if the ground is saturated, what does that mean?
That's wet.
It's very wet. It means like if it rains some more, that rain isn't going to go into it. Yeah, exactly. And that's what saturated air means. It means like even if water vapor tries to go and evaporates into it, it's just going to kind of condense back out. It's done. So, exactly. So these were the figures I was talking about. Now, on these figures, I think they are so adorable. This is actually kind of time zero. Do you have all these figures? Yeah, I think you did 3 figures. So, this is liquid water, and this is actually no gas up here. And this little thing I circled is a pressure gauge. but it's selective for water vapor particles. So basically it's pegged out. There's no water vapor particles making that pressure gauge go up. So if you allow a little bit of time, okay, what's going to naturally happen, and it's a little bit random, okay, kind of depending upon T, the temperature of this liquid. Some of those little liquid water particles are going to get enough energy, they're going to break their bonds, just like you see those 3 ones, wee, we're free. Okay, they're going to break their bonds and they're going to start to zoom around in there. It just will. And so of course you see the pressure gauge go up. So pressure is a thing. It's a real thing. Okay, so pressure goes up. But notice that we have kind of your row child. So we have evaporation, we have condensation, but they're not equal. Basically, we're showing 3 up, 1 down. Okay, so it's not saturated. It's still more evaporation than condensation. It's undersaturated. Well, again, kind of going back to your terrarium, if you allow it to kind of do its thing, basically it's going to reach a back and forth point where the amount of evaporation is equal to the amount of condensation. And that's this last case. So yeah, we have 5 and 5. Okay, and notice the gauge, it tipped even more over. So actually, and I'm going to show all of these. Let's kind of take a look at these terms. Of course, you're okay with evaporation. Evaporation is liquid going to a gas. Condensation is gas going to a liquid. Now, the vapor pressure is up here. Okay, you need to kind of think of vapor pressure as basically those water molecules kicking, okay, which they're doing in this room. Saturated air only applies to, I guess I'm not pointing to that, right? Only applies to this, right? Saturated air. Okay, so then actually we have a special vapor pressure. So this right here is saturation vapor pressure. Yep. Those other ones, not quite. Okay. So vapor pressure. So in this class anyway, when you hear the word vapor pressure, I just want you to think of water vapor pressure. Even though nitrogen has a vapor pressure, oxygen has a vapor pressure, argon has a vapor pressure. Okay. So the vapor pressure, if our goal was to increase or decrease the vapor pressure, we could do a couple different things, and I bet you already know what they are. One is we could change the kinetic energy of the particles, of the vapor particles. Okay? If I were to go over here to that last box, and if I were to jack up the temperature, you tell me those things would go faster. And if I had a pressure gauge on top there, pressure gauge would kick over too. Okay? So that's one thing. The other one is just to add more. Again, with that last box, if I go over here, and I love, physical science. A lot of things in physical science is very intuitive. If I were to go over here, and I was to go ahead and add 4 more particles, okay, that's actually going to make my pressure go up, even if they're at the same temperature. They're just kind of collectively. That's actually what we do when we blow up a balloon, okay? When you're exhaling into a balloon, basically you're adding more and more. It's not water vapor, but it's gas from your lungs. Okay, and you're increasing the pressure. So those are 2 ways to increase the vapor pressure, water vapor pressure. So actually shown here are both of them. It's funny, if you go ahead and take your terrarium and heat it up, okay, you're actually going to increase the kinetic energy of these guys. So they're going to be ramming around. But you're also going to increase the evaporation. You're going to put more of them. You're going to change the dynamics. Okay, and you are actually going to end up with more in your vapor state from their liquid. So, all right. So this actually is in chemistry what we call an equilibrium vapor pressure curve. You guys remember that 3rd box a little bit ago that was at saturation, equilibrium, both of those things for that 3rd box, okay? That up there, that dial, was indicating a pressure of water vapor pressure. And that actually you would find on here. at the given temperature of your terrarium, okay? So the way this works is, if you notice this is increasing your temperature, if you increase your temperature, what happens to your saturation mixing ratio? It goes up, exactly. These are, remember what we said, a mixing ratio was grams of water vapor to kilogram of dry air. That's exactly what that is. Yep. Here's another one for you, and we're going to talk more about this. Have you ever heard that cold air holds less water than warm air? Ever heard that? Cold air holds less water. There is something to be said for that. Let's look at this in that regard. So this is cold air, okay? Like if you're over here at minus, oh my gosh, minus 20 degrees Celsius, okay? This actually is your saturation mixing ratio versus a plus 20, okay? Your cold air holds less water vapor. These are saturation mixing ratio amounts. All right. So that curve in a table form is right here. Did you guys have something to fill in there? Are you okay? Okay. Good. So if we were to take that curve and kind of tabulate it, this is what it looks like. So I think I have an arrow. And we're going to pick on, actually here in a minute, I think, we're going to pick on the temperature of 25. So let's prove to ourselves. This says as you get warmer, okay, warm air holds more water vapor. I know it doesn't work that way. My husband also teaches chemistry, and he's like, no, water or air doesn't hold water. It just kind of allows it to be so. But really, you do get more water, grams of water vapor per kilogram of dry air if the temperatures are jacked up. Okay, so the magic tipping point, if you're at 25 degrees Celsius, is at 20 grams of water vapor per kilogram of dry air. You are at saturation. So you're not going to get 21, you're not going to get 22. It's done at that temperature. Although there's something called supersaturation. We'll talk about that. Okay. All right, so relative humidity is basically it's how close you are to being saturated. It is your actual water vapor content divided by, comes from a table, divided by basically how much at that temperature water can be held in the air at that temperature. So the bottom one you get from a table at that temperature, the top one you go ahead and measure. Okay. So like we know, we're kind of run into percent relative humidity, I'm sure, before. The closer you bump up against 100% relative humidity, then you're bumping up against saturation. That last, those 3 boxes I showed, the third box was 100% RH. Saturation is 100% RH. Okay, so how are you going to change your relative humidity? Well, it kind of goes back to how are you going to change your vapor pressure, your water vapor pressure. You can either change the amount of water vapor in the air, or you can monkey with the temperature. Now what I say is if you adjust the temperature, like, okay, if we cool this down, we know that you can get, I put it in the wrong place. If we cool this down, we know that we can get condensation to happen. Okay? We know that we can push ourselves to 100% RH. Here's the deal. As you cool it down, you are going to get a new, this is the way I look at it anyway. As you cool it down, you're going to get a new table value. New table value with changing temperatures. Okay? So that's kind of how it keeps, you're just keeping dividing by a different number as you're changing the temperature. All right. So So remember a little bit ago, I said on the table to kind of highlight the 25 degrees Celsius. Remember on the table we said you max out at 20 grams of water vapor per kilogram of dry air. So coincidentally, I like these three things we're going to see. They all have 1 kilogram of dry air, and they're all going to hold at 25 degrees Celsius. Okay. So, do you see where the percent relative humidity value came up? Oh, I should add. I didn't add this. The other piece of information you need to calculate percent RH is if it can hold 20 grams, which is from the table, how much water vapor is there in that 1 kilogram of dry air right now? 5. Your author's saying 5. How did he get that? Well, we can ask him. Okay? But he got 5. So if you take what's there, 5, divided by how much it can hold, 25, sorry, how much it can hold, 20, okay, then you get 25%. Okay? So now what we're going to do is see the orange right here? That's the number that's going to change. Well, actually, then the third number will change too. They, for however reason they're doing it, they are going to, maybe they took a little syringe and injected more water vapor in there. Maybe they let it sit, I'm not sure. But now when they come back, maybe they're just kind of letting it turn into a terrarium, okay? When they come back later, this headspace above this liquid now, instead of 5, it's got 10. So it's the same temperature, so if we want to go ahead and calculate the relative humidity, it's what it has, 10, divided by what it can hold, which is 20. So it's 50% RH. And then come back later, yeah, this does look like it's kind of reaching saturation, doesn't it? Because there, the last one, it's got 20 grams of water vapor. 20 grams is what it has, 20 grams is what it can hold at that temperature, so it's at 100% RH. Not bad. So that example that we saw was basically holding the same temperature. So in your percent RH calculation, if you hold the same temperature, the bottom number, which was 20, did not change. And what they changed was the top number. So ways that we kind of take an environment and inject more water vapor into it. For instance, in a shower, the thing about showers is it's nice warm water and it's like almost vaporized, like a lot of surface area, and so it goes from a liquid to a gas. So your bathrooms basically increase in their water vapor, and you can go ahead and reach 100% relative humidity. If you see your breath on a cold winter day, you're actually seeing a cloud, in a sense. It's milky white because actually water vapor from your lungs is liquefying, okay, in the cold. So what you're doing in that case is you're taking cold air that was minding its own business, no cloud there, and you're just increasing the water vapor. So you're reaching 100% relative humidity at that temperature. One of my favorite things in the summertime are those short showers, you know. If they bring a few thunderstorms and then go away, that's kind of fun. But in the summertime, if the sun's been shining, and for instance, if you think of black pavement, if you're at Adventureland, a lot of black pavement, okay, it absorbs a lot of radiation. Then we get our showers, and that rain goes ahead and hits the hot black pavement, okay, and then from the hot black pavement, basically that can go ahead and vaporize some of that liquid. And so kind of right above that hot pavement, you have saturated. You have a lot of water vapor that's injected, and it can go ahead and form those little clouds. Okay, so one more thing, well, for right now. So we're going to see 3, I don't know what sort of flat bottom flasks again. 3 little pieces of glassware up here. And they're going to be at these 3 different temperatures. I think it's going to start at the higher temperature, 20 degrees Celsius, then go to 10, and then go to 0 degrees Celsius. But the thing here is that notice that on the right here, that at 20 degrees Celsius, 1 kilogram of dry air can only hold 14 grams of water vapor. At 10 degrees Celsius, it can only hold 7. At 0 degrees Celsius, it can only hold 3.5. Okay. So here we go. 7 grams of water vapor. Okay. at 20 degrees Celsius, if we wanted to go ahead and calculate what was the percent RH, we'd have to use the table. That first number comes from the table. We'd have to look up 20 degrees Celsius, and we'd see that its mixing ratio at saturation is 14 grams of water vapor per kilogram of dry air. We are given 7, so we divide 7 by what it is, by 14, what it can hold at that temperature, and you're at 50%. We go ahead and we keep the same 7 grams, but we lower the temperature from 20 to 10. So the thing that's going to change now is from the table. At that temperature, you got a different number. It's mixing ratio, saturation mixing ratio. So now we still have 7, so wow. So what it can hold, or what it is, which is 7 divided by what it can hold, which is also 7, you're like, dude, that's 100%. So what happens when you cool it down even further? Okay, well, it's basically going to go ahead and rain. Okay, at that point, as you go from 10 to, if this is saturated, if you cool it down even more, okay, then some of the water vapor is going to have to come out. When the dust finally settles at 0 degrees Celsius, and you're going to go ahead and it's still going to be saturated, but now notice that at that cooler temperature, how many grams of water vapor can 1 kilogram of dry air hold? And the answer is, according to the table, 3.5. Okay, so you had 3.5 come out, and you had 3.5 stay in. Very symmetrical. Okay. So bottom line, if your goal is to have saturated air, okay, well, the closer air comes to saturation, the more likely you are to get condensation or even solid water to form. So if your goal is to reach 100% relative humidity, you can lower the temperature like we saw in that last example, or you can increase the water vapor like we saw in the first example. Got one of these. Okay, well that's a good time for a break. So let's take a break.